Machine learning has revolutionized how we approach the data-driven decision making with algorithms that allow the machines to learn predictions and patterns. Among the various algorithms, decision trees stands for its simplicity and effectiveness in both classification and regression. So welcome to the session on decision tree. In the series of lectures on decision tree, today's session we will see the theory behind decision tree. We'll try to understand the ID3 decision tree algorithms, and in the next session we'll discuss problems on how we can construct a decision tree. So let's begin. So let's understand what is a decision tree. So decision tree is one of the most popular supervised predictive learning model used for classification, actually also for regression. It helps to classify data instances with high accuracy and consistency. Decision tree performs inductive inference. In the sense, you can use decision tree, or it's a process where you can draw conclusions from specific observations. Decision trees are mainly used for classification applications. It's a concept tree where we summarize the information which is there in the training data set in the form of a tree structure. So given a training data set, which consists of various attributes, and finally you might have to do some kind of a classification. So the training data set we are going to transfer into a tree, which we call it as a decision tree. See, once the tree is constructed, you can use the decision tree to do the classification on the test data. So using the training data, you construct the decision tree, and once it is constructed, you can use the decision tree to do classification for your test data. So basically, decision tree can be used to classify categorical as well as continuous value target variables. So let's say I have a training data set X, right? And this model, let's say it computes a hypothesis function f of x as decision tree. The input to this model will be the data instances with set of features or attributes, and the output is basically, it will tell, the decision tree will tell whether it can predict or classify it will predict or classify the test object into a particular class. So the input to the model will have certain features which are independent variables, and the output is basically a class which will predict the test object. So decision tree learning model will generate a complete hypothesis space in the form of a tree structure for a given training data set, and allows us to search through the possible set of hypotheses in the decision tree. So this kind of search, where we search through the decision tree, is called as a preference bias. So let's see the structure of a decision tree. The root node is indicated through a circle like this. So basically the root node is the topmost node of the decision tree. So the second figure shows an example of a decision tree. So this is the root node, which is the topmost node in the tree, which represents the entire data set. The root node is further split based upon the most significant attribute. The nodes which we have at the end of the decision tree are called as the leaf nodes. So there are also the terminal nodes, which basically represent the final classification, or the leaf node will finally tell which class the test data belongs to, or it is the output node. You cannot further split the leaf node, so that is the terminal node or the final node. Splitting. Now splitting is basically a process where we are dividing a node into subnodes. So this is a root node, and these you can also call it as subnodes or internal nodes. So the splitting basically is a process where you branch out the node into further subnodes, and the branching or the splitting basically will be done based upon a decision. So the decision node can be represented through a diamond like this. In some cases, in some diagrams, the leaf node are represented by rectangles. In some diagrams, they are also represented as circles. Both are fine. So branch. So these are the branches. So branches are basically represent the subset of the data that results from splitting. So it leads from a parent node to a child node or a leaf. Decision node. Now decision node is a node that represents a decision to split the data further based on a particular feature or an attribute. So here in the internal node you make a decision based upon which how you can split it into further nodes. So this internal node can also be a decision node. Now I'll be using the word pruning many times when we are constructing the decision tree structure. So pruning is actually a process where we are removing parts of the tree that are not contributing to the model's accuracy. So pruning is a process of cutting down or removing a parts of the tree which are actually not contributing for the model's accuracy, and therefore by pruning you can prevent overfitting. So let's see how we can build a tree. So before we build the decision tree, you have to establish the goal. What is the goal for constructing the tree? So first thing is you have a training data set which can be, let's say, in the form of an Excel sheet with some attributes and some values for every attribute. Now looking at that, you start constructing a decision tree in a top-down fashion. First you have to establish from where you have to start. So the start will basically establish your root node. Then at every level you make a decision. What is the best decision? What is the best split or best decision you take in order to form the subnodes? So basically you will observe that this will be a recursive process. The next question is, when you are constructing the tree, when do you stop growing the tree? That would be very important. So we can stop growing the tree based upon certain conditions. Maybe that we end up in a last level, we end up in a node which cannot be further split. So when the node cannot be further split, that can be one decision. Or a second decision would be all the test conditions have been satisfied. All the conditions you have checked in your training data set and you have made your leaf nodes. So based upon that you can stop growing the tree. So as I said, leaf node is basically your final output node which will tell which is the target class or the output of your classification. Now basically what is the output of your tree? The output of your tree is nothing but your decision. Output is basically you will finally have a decision tree which represents your complete hypothesis space. So remember, this decision tree need not be a binary tree. In the sense, a node need not be branched like this into just two. You can have many branches. A node can be split into more than two branches. So basically it's not always a binary tree. You can have more than two branches. So what's the process of forming a decision tree is, the goal you need to first define, given a test instance, infer to the target what target class that it belongs to. Now how do you start building the tree is, look at what your class is for your test instance, and then you start traversing your tree from top down approach. First establish which is your root node, and then at every decision making you need to check based upon a decision how we are going to do the branching, and this process will repeat until we reach the leaf node where you can further, after that node you cannot do any more splitting. So that would be the end of your node. So the final output would be, output of your decision tree would be a target label for your test instance. When you give a test data set to this decision tree, you should be able to classify to which instance this test data belongs to. So what are the advantages of going for decision tree is, first of all, it's very easy to model and interpret. You can interpret the decision tree easily. It's very simplicity. That's decision tree is known for its simplicity, and you can also use it for discrete as well as continuous values, and you can model a high degree of non-linearity in your relationship between the target variables and the predictor or the output variables, and very easily and quickly you can train your data set using decision tree. The disadvantages are, it's difficult to determine how deeply your tree can grow or when to stop. So when you are actually working, you might have initial some kind of a problem in finding out how much your tree will grow or when to stop. And the second disadvantage is, if the training data has errors or suppose they are missing attribute values, then your tree can be unstable or biased. The third problem is, if the training data set has continuous values, handling it can become computationally complex, and therefore it has to be discretized again. The fourth one is, a complex decision tree can result in overfitting issues, And the fifth issue is decision tree is not well suited when you're classifying multiple output classes. It's very good for 2 or 3, but when you have like 10 classes, then it's not really ideal. The sixth one is learning an optimal decision tree is also known to be NP complete. So really coming up with an optimal decision tree can be an NP complete problem. So let's look at a simple example. Suppose this is a training data set which is given, and the attributes are, you have for a student assessment, you are basically predicting whether a student will pass or fail based upon the assessment marks and the assignment marks. Okay, so this is a table which is given. So let's first decide which is going to be a root node. So let's say I choose my assessment as my root node. So then I make a decision if the assessment is greater than or equal to 50, or if the assessment marks is less than 50. Based upon that, then I check what about the assignment. If the assignment is yes, then pass. If the assignment is no, then again you say it is fail. So let's say this is the algorithm. If the assessment marks is greater than or equal to 50, then let's say I will say quickly decide it's for pass. If the assessment marks is less than 50, then I am going to check the assignment. If the assignment is yes, then I will say pass, else I will say fail. So based upon this algorithm, this is a decision tree we have come up with. So what here is assessment, this one is the root node, these are the rectangles represent the leaf node, and this diamond represents the decision node. Some cases you will see that all the nodes are represented as circles, both are fine, but in this case what we are seeing is root node is denoted with a circle, decision nodes are represented with a diamond, and the leaf nodes are represented with the rectangles. So now, before we get into a particular algorithm, let's understand the concept of entropy. Now the question is on what decision I'm going to split up the tree, right? So the one very important attribute is we are going to split the data set based upon how much information it has. So when we talk about information, the term that you should get into your mind is entropy, right? So in Shannon theory or information theory, we have learned that quantifying information is very closely related to information theory, and Shannon entropy is all about how you quantify your features by a measure. So quantification of features by a measure, that's called as Shannon entropy. So Shannon entropy is a term, or you can say a metric which is used to which we calculate based upon the probability distribution of events. So before that, let's understand what is entropy. So basically entropy is the amount of uncertainty or randomness in the outcome of your random variable or event. So entropy basically describes what is a homogeneous how homogeneity is there in your data instance. So the best feature is selected based upon the entropy value. So we are going to do splitting based upon the entropy value. So let's say I flip a coin. Head or tail are the two outcomes, right? Entropy is lower when when you're comparing it with the rolling of a dice. So if you compare the flipping of a coin with the rolling of a dice, then entropy is lower in the case of a coin as compared to dice, because the number of outcomes for a coin is 2 and the number of outcomes for a dice is 6. Let's take another instance. Suppose all the instances are homogeneous. Let's say 1 or 0. Suppose I have all the instances belonging to the same class. Then the entropy is 0. So suppose I flip the coin 5 times and every time I get head. So I'm getting a homogeneous instance where the entropy is 0. Suppose I get 50-50. Suppose 2 times I get head and 2 times I get tails. Then the entropy is 1. And or suppose I have 10 data instances where I have 6 instances belonging to class 1 and 4 belonging to class 0, then you have to calculate entropy using this formula, and this is a formula which we are using to calculate the entropy. So what is important is higher the entropy, higher is the uncertainty. Lower the entropy, lower is the uncertainty. So what are the key things that you need to remember is, if the data set as instances which are completely homogeneous, that means you're going to get only one. Let's say I'm always going to get heads, then the entropy is 0. There's no information. If the data set has equally divided instances, say 50-50, then the entropy is 1. So what you have to remember is when you're calculating entropy, it will always be in the range of 0 to 1. Okay, so if entropy is 0, then the split is pure. All samples will belong to one class. If entropy is 1, then the split is impure. The distribution is very random. And how do you do the stopping criteria for your decision tree is now based upon the entropy value. So in next classes I'll be doing algorithms where we are going to decide the stopping criteria based upon the entropy value. So let's see the math behind this. Suppose I have P is the probability distribution of data instances from 1 to n, that is P is equal to P1, P2 up to Pn. Then the entropy of P, that is the information measurement for this probability distribution, or the entropy information for all the probabilities P1, P2, Pn is minus of P1 log P1 plus P2 log P2 up to Pn log Pn. So P1 is a probability of data instance classified as 1 belonging to class 1. P2 is a probability of data instance classified as class 2 and so on. So basically, how do you calculate P1? So P1 is calculated as number of data instances belonging to class 1 divided by total number of data instances in the training data set. Now going back to this problem, this is how we got. This is P1 log of P1 plus P2 log of P2. So what is P1 here? P1 is number of instances belonging to class 1, that is 6, divided by total number of instances, that is 10. And here again P2 is number of instances belonging to class 2, that is 4, divided by total number of instances 10, log of again 4 by 10. So this is how you calculate the entropy. Okay, so this formula you need to remember when we are working on problems. So let's discuss about the general algorithm for decision trees. So first step is you have to decide which is the best attribute, right, to be chosen as the root of the tree. So when you are constructing your decision tree, first select which is your root of the tree. So once you have selected the root of the tree, now you have to decide on what basis I'm going to split the root of the tree. And the third step is I will go on repeating this step in 1 and 2 until we get the leaf nodes of our tree. So what you realize that the splitting of the nodes will be a recursive process. So the main thing that you need to decide is when you are going to stop. So the stopping criteria for your decision tree is finally either you will finally be coming up with nodes which all belongs to the same class. That means finally you will be having entropy as 0. Or second case is a node with some defined minimum number of data instances. Suppose I have decided, okay, this is the number of leaf nodes I am going to have. I am just going to have 4 leaf nodes. So you can stop there. Or the third one is the maximum tree depth is reached. You define this is the depth of the tree that I am going to have. So once you decide that, you can stop the splitting. So what you observe here is based upon any of these 3 conditions, you can stop growing the tree. So just to quickly revise, if you are no longer able to split your leaf node, that can be one condition. Or you have decided that this is a maximum number of leaf nodes that I'm going to have, or this is a maximum depth of my tree that I'm going to have. So based upon any of these 3 conditions, I'm going to stop the growth of the decision tree. So there are different types of decision tree algorithms like ID3, C4.5, CART, CHAID, Quest, Guide, Cruise and CTREE, and the most common ones are ID3, C4.5 and CART. So in the next few sessions we will be discussing about each of these algorithms and we will be doing problems on this. So let's meet in the next session where I will be discussing about the first decision tree, that is ID3 tree construction. We will discuss the algorithm and we will do a problem on this. Thank you so much and please subscribe to the channel.